Picture a long drawer in a celestial records office sliding open, dust motes floating like tiny worlds, and a worn folder labeled visitors from elsewhere. Inside, notes, sketches, and patient predictions waiting for a suspect to match. Then, one quiet night, a new streak appears in the star field. The clerk of the cosmos stamps the file. Case reopened. Meet our traveler. 3I/Atlas is not a local. It did not punch a time card at the sun's gravity well. It did not grow up in the neighborhood of the outer planets, learning the usual routes past the ice giants and back. This thing is the cosmic equivalent of a tourist with a one-way ticket and a very confident stride. Interstellar means it comes from beyond our family of planets, from the black ocean between stars, where distance turns braggy and cold becomes a lifestyle. Think of it as a message in a bottle tossed from a far shore, bobbing through the galaxy until it washes up on our beach. Earth is basically a rock that won the cosmic lottery, and part of the jackpot is getting to read messages like this. The name tells a tidy story. The 3I tag means it is the third recognized interstellar object to wander near the sun since modern surveys started catching such things. The second part, Atlas, points to the survey that spotted it, a system that scans the sky every clear night, like a lighthouse with a photographic memory. You know that friend who notices when you moved the living room lamp 3 centimeters? Atlas is that friend. But for stars, when a new point of light does not behave, alarms ring, astronomers caffeinate, and telescopes swing. Now, about that path. If you could trace the comet's motion on an invisible pane of glass laid over the night sky, you would see a graceful curve that never closes. It is a once-through signature, a hello and goodbye written in momentum. Imagine throwing a stone past a campfire and hearing a brief sizzle as it arcs by without stopping. That sizzle is the sun's heat waking up the comet's ices, painting a tail and a fuzzy shell. But the trajectory itself says everything. This traveler is not bound to come back. No ticket to return, no loyalty program with the sun. Black holes are the universe's way of saying delete browsing history permanently. Hyperbolic paths are comets, saying do not bother saving my seat. Here is the detective twist that makes headlines sing. For generations, sky watchers proposed that if the galaxy is busy building stars and planets, then every so often the leftovers must be flung into interstellar space. Those leftovers would sometimes drift into our view. They would not loop like regular comets from the distant cloud that surrounds the sun. They would spear through on near straight lines, barely tipping their hats. 3I/Atlas is that hat tip, delivered with a flourish that seems almost theatrical. It is the feeling of finally meeting someone you have only known from letters. But do not mistake the elegance of the curve for simplicity of the story. The discovery kicked off a quiet stampede. Observatory logs filled with time requests. The American Space Agency, European teams, and university groups lined up observations, knowing that every hour matters when a visitor is moving fast and fading. If you have ever tried to recall a dream before it evaporates, you have the idea. Catch the details now, or lose the thread for good. Photos were taken in crisp bursts. Spectra, which are like barcodes of light, were recorded to read what the comet is made of, and the orbit was refined over and over, each night tightening the certainty of the path, like sailors updating a map mid-voyage. What makes this especially fun is the mood whiplash. On one hand, it is a familiar sight, a fuzzy wanderer growing a luminous tail as it approaches sunlight. On the other hand, this fuzzball carries a passport stamped by another star. It is like seeing your everyday coffee shop and realizing the barista is secretly an award-winning chef from another country. Same aroma, wildly different backstory. Photosynthesis is plants' way of saying we invented solar panels first. Comets are the universe's way of saying we perfected freezer technology ages ago. There is a human angle too. Picture the people behind the data, a night operator checking focus as the dome whirs open, a graduate student writing code that blinks 2 images and circles a tiny moving dot. A veteran astronomer who has been waiting decades for this exact kind of motion to appear in the numbers. Science sometimes moves like a glacier, but nights like this feel like a drum solo. The trick is to ride the rhythm without getting sloppy. That means clear reporting, open data, and patient verification. The sky rewards humility. It also rewards good snacks at 3 in the morning. What does a visitor like this give us in the first act of our story? A compass setting. It tells us the direction it came from on the sky, hinting at the sort of stellar neighborhoods that might fling out icy bodies. It gives us a timestamp on its closest brush with the sun, a date astrophotographers scratch into calendars with big circles and excited doodles. Most of all, it hands us a clean example of how a traveler from afar looks when it is just doing its thing, unbothered by wild swerves or surprise loops. That baseline will anchor everything we ask later. So, file the first report. A stranger announced itself. The instruments listened, and the path lined up with what careful minds long suspected. Our cold case did not just warm up. It stepped out of the shadows with a name tag and good lighting. Next time, we will ask the sharper question, what exactly makes an object truly interstellar? And how can you tell at a glance that it is not one of ours? Chapter 2. What makes it interstellar? Start with a picture in your head. You are standing at the edge of a deep valley with a skateboard and a ramp. If you roll down the slope and do not push, you might coast up the far side and settle back somewhere in the valley. That is a bound trip. If you add just the right kick at the bottom, you reach the top and stall out. That is the borderline case. But if you charge in with extra speed, you sail over the rim and keep going into the next county. That last move is our visitor's calling card. Interstellar status is simply this. It came in fast enough to climb out of the sun's valley and never look back. The universe loves drama, and this is the cleanest kind of dramatic exit. Astronomers describe paths around the sun using a family of curves with very different personalities. A circle is the chill roommate who never leaves. An ellipse is the commuter who takes the same loop again and again. A parabola is the traveler who arrives with exactly the minimum speed to reach the mountaintop and then fade into the far plains. And a hyperbola is the long-haul driver who blows through the toll booth and vanishes down the highway. Our interstellar guest is that driver. Hyperbolic means the object is not gravitationally bound to the sun. It came from outside and will head back to outside. No return ticket, no summer sequel. How do we know it is not secretly looping in a gargantuan oval that would bring it back in some far future age? The shape tells the story. Ellipses, even very stretched ones, are closed paths. They are loops, however skinny. A hyperbola is open. Trace it with your finger, and you never meet your starting point. Think of a boomerang versus a javelin. A boomerang bends to come home. A javelin slices past and disappears behind the stadium seats. Interstellar visitors are javelins. The key idea hiding in that shape is energy. In a gravitational field, the total energy decides whether you are trapped or free. Bound orbits have negative energy compared to the effort it would take to escape. They are like marbles in a bowl. A parabolic track is right at the rim of the bowl, no extra energy to spare. A hyperbolic track has positive energy. You can think of it as extra fuel in the tank. The sun tries to decelerate the newcomer, and does, but not enough to hold it. Picture a roller coaster that starts from outside the park with a head start. It screams through the loop and shoots straight out the exit, leaving the souvenir shop untouched. Thrilling and very bad for the gift shop economy. Another giveaway is speed. Every distance from the sun has a certain escape speed, which is the pace you need to leave and never be pulled back. Interstellar objects arrive already above that local limit. That is why astronomers love the phrase slingshot and never coming back. The sun does act like a slingshot here. But the passenger brought its own momentum. The curve bends, the tail glows, and then the visitor is gone. It is a mic drop in celestial choreography. Direction also matters. Long-period comets that belong to our distant, icy reservoir tend to arrive from random skies. But, taken together, they tell a story of a spherical cloud bound to our system. Interstellar guests are not drawn from that club. Their incoming direction has no duty to match patterns set by our family. It is as if a parade of neighborhood cyclists rolls in from familiar streets, and then a motorbike roars out of a hidden mountain road, dust plume and all. You do not need a badge to know it is not from around here. Now, you might wonder, could a local comet fake a hyperbolic path by getting a wild kick from a planet? Planetary flybys can indeed tweak a track, but those cases have a very different fingerprint. A local comet that picks up speed from a planet generally reveals that close brush in its past path, and the hyperbolic excess is small, like a free upgrade to Economy Plus. An interstellar traveler shows up already holding a first-class ticket. The numbers are not the point here. The concept is, one story is a neighborhood push, the other is a long journey from outside the neighborhood entirely. Here is a helpful way to feel it in your bones. Imagine the sun's gravity as a campfire in the tundra. Bound comets are snow wanderers who circle the fire every winter, sometimes close, sometimes far, but always returning to warm their orbit-chilled faces. A parabolic comet is the wanderer who steps close once, fingers outstretched, and then drifts away on the wind. An interstellar comet is a passing sled team that races by, sparks flying from the runners, leaving only swirling snow and a fading howl. The fire glows the same for all, but only one group is just passing through. Evidence piles up from the way the light behaves too, but not in a way that demands math. When a visitor arrives with surplus speed, its timeline is compressed. The brightening and fading happen on a schedule that matches a quick flyby, rather than a leisurely loop. Observers know to treat it like a fireworks finale. Enjoy the moment, because the curtain drops fast. There is something poetic about that tempo. Interstellar objects teach us patience by refusing to give us any time. This is also why the phrase interstellar object is more than a headline hook. It signals an origin story beyond our sun's nursery. The ices and dust were cooked under different neighborhood rules, around a different star, with its own storms and seasons. The hyperbolic path is not just a shape. It is a signature that says forged elsewhere. If planets are the finished meals, these visitors are the grocery lists from other kitchens. In short, what makes it interstellar is not a vibe or a rumor. It is a specific geometric truth, an open path, a surplus of energy, and a speed that shrugs off the sun's pull. The image to keep is simple and trustworthy. Slingshot, glow, goodbye. The universe stamps the passport on the way in and again on the way out. Next time, we will translate that passport into plain language, the centuries-old prediction that such travelers would cut through our sky on open paths, and why that idea sat waiting so patiently for a match. Chapter 3. The Old Prediction. In plain English, imagine a grand chalkboard stretching across a 19th century lecture hall. Lamps hiss, coats rustle, and a quiet figure with an ink-stained cuff sketches a curve that never quite closes. The audience cannot see the entire story in one glimpse, but they grasp the punchline. If a wanderer from deep space ever breezes through our neighborhood, it will look, to the patient eye, like a near straight-through flyby. No loop, no second act, just a graceful pass that says passing through, mind the dust. That was the heart of an old prediction from the age of quills and brass telescopes, and it is the reason our modern visitor feels like a letter delivered to the right address after 2 centuries in the post. Let us translate the old idea without the museum dust. Early celestial mechanics thinkers, including the careful mind of Pierre-Simon Laplace, asked a simple question. If the sun holds onto some wanderers but not others, what would a true outsider look like when it first appears in our sky? They did not have digital cameras or global networks. They had nightly positions scratched onto paper and the stubborn habit of checking their sums twice. Their answer came from common sense dressed in mathematics. A traveler that is not bound to the sun does not trace a loop. It cuts across the map. Seen from Earth, that crossing looks almost like a straight shot, which astronomers of the day would often approximate with a special borderline curve that was easy to compute with the tools they had. Why almost straight? Because the sun still tugs. Even a free passerby bends a little as it swings nearest the light. The old prediction did not say the path would be a ruler line. It said it would be so open that over the limited nights available, it would masquerade as that borderline case. Observers in the 19th century routinely fit new comets with this borderline track first, because it was simple and worked surprisingly well for short arcs of data. Picture a town historian who, lacking aerial photos, sketches the main road as arrow straight, because from the porch it looks that way. The road might bend over the hill, but from the porch, the shortcut works. This habit of first guessing a near straight-through path was not laziness, it was strategy. Consider the tools. Telescopes then were precise for their era, but still at the mercy of wind, glass, and human hands. Timekeeping was good, not perfect. Positions were measured against star charts that took heroic effort to assemble, with only a few nights of dots to connect. The safest call was to assume the simplest shape that did not tie the comet to a repeat performance. If later measurements demanded otherwise, the mathematicians would adjust the sketch. It was a disciplined dance. Start with the easy outline, then refine. Here is the clever twist baked into that approach. The borderline curve sits exactly on the fence between guests who will stay and guests who will leave. So starting there means you are acknowledging your ignorance honestly. You are saying, in effect, this might be one of ours, or it might be a drifter, until the numbers speak more clearly. I will give it the most unbiased runway. It is the scientific version of not picking teams until everyone arrives on the field. Also, it saved time, and in astronomy time is the one thing the night always takes back. Laplace and his peers were not just solving puzzles for sport. They lived at a moment when the sky was turning from mythic canvas into a system you could test. They realized that a universe full of stars must, by sheer numbers, toss some icy debris into the spaces between. Every star that grows planets has leftovers, and some leftovers are flung outward. Occasionally, those exiles wander near us. The prediction, then, was not a prophecy or a guess. It was a consequence of a busy galaxy. If the heavens behave like a restless workshop, the shop floor will have sawdust, and some of that sawdust will drift under our door. The cultural mood helped. This was an era enthralled by navigation, clocks, and steam. People trusted that patient measurement could tame even the wildest stories. Comets, which had once been omens, were becoming case studies. When a new smear of light appeared, the community would trade letters, publish elements, and debate whether the track belonged to the familiar family of returning visitors or hinted at something stranger. Behind the arguments was that steady expectation. A truly foreign traveler would reveal itself by refusing to close the loop. It would look, for a while, exactly like that borderline shape on the chalkboard. Leap forward to our century, and the old chalk line meets a real sky trail. 3I/Atlas arrives, and as data stacks up, the path aligns with that 19th century expectation, an open crossing, a clean refusal to become a repeat customer. The surprise is not that the past was brilliant. The surprise is how enduring that practical logic feels when modern detectors flood us with crisp, timed images. It is like hearing a symphony played on a period instrument and realizing the melody still lands perfectly in a cutting-edge hall. What does this teach us about the practice of science? That predictions built from principles can outlive the tools that first tested them. The golden rule here is not trust the old, but trust what keeps earning trust. When a fragile idea meets new evidence and still stands, you are not watching nostalgia. You are watching durability. It is oddly funny, too. We love flashy breakthroughs, but the stars keep rewarding the people who write things down, argue about them politely, and turn up again the next night. Space loves drama. Science loves paperwork. There is another quiet lesson from the old playbook. Resist the urge to decorate the unknown. The early observers resisted dramatic claims because the sky already provides drama. They aimed for shapes that could be defended with a season's data. That discipline traveled across centuries and helped us recognize our visitor for what it is, not for what a headline might wish it to be. Comets do not care about our metaphors, but they do reward our habits. So the chalkboard closes, the lamps dim, and the idea walks off stage with a small, satisfied smile. The prediction did not need a parade. It needed a match. 3i/Atlas provided one, and the match burns clean. Next up, we move from blackboard to control room. How the modern pipeline catches a faint speck, strings together positions, and turns a scatter of nights into a confident path you could set your calendar by. Chapter 4. How we actually measure a new orbit. Fade in on a quiet control room. The lights are low, monitors glow, and a technician clicks a button that makes two images of the same star field blink back and forth. Everything stays put, except one faint speck that hops a hair's breadth from frame to frame. That hop is the first heartbeat of a new orbit. In that instant, the sky becomes a connect-the-dots puzzle, where the dots are nights and the line is a path through the solar stage. Space may be silent, but discovery sounds exactly like a keyboard and a whispered, "There it is." The opening move belongs to the survey telescopes. They sweep the darkness with wide eyes, collecting snapshots like a diligent night watch. Each pixel is weighed, cleaned, and compared to star maps, so precise you could navigate a gnat across the Milky Way. A small software scout scans for anything that shifts between exposures. Cosmic rays, airplane flashes, camera ghosts, those get tossed. What survives is a short list of candidates with the right kind of motion. Think of it as space paparazzi. Most blips are false alarms, but every now and then you catch a genuine celebrity sneaking across the carpet of stars. For each promising speck, the pipeline extracts astrometry, which is a fancy way of saying pinpoint positions on the sky, with timestamps. The coordinates are corrected for effects that would make a navigator grumpy. Atmospheric refraction, distortions from the telescope optics, and the subtle wiggle introduced by Earth's own spin and track around the sun. The positions are then tied to a modern star catalogue, so the whole sky speaks a consistent language. The result is a small table with rows that read like diary entries. On this minute, at this place, the object stood here. Those diary entries fly to a public clearinghouse where measurements from different telescopes can meet. Within hours, other observatories join the chase. A robotic scope in the desert confirms the motion before dawn. An amateur in a backyard, halfway around the world, adds a pair of clean points after dinner. The magic is not just more data. It is data taken from different places on Earth, which gives a helpful touch of parallax. It is the same trick your brain uses to judge depth when you look with two eyes, only now the eyes are continents apart. Enter the orbit solvers. These are code libraries and web tools that take the scattered positions and ask a simple, brutal question. What path through space would pass all these checkpoints at the recorded times? The first answer is rough. It is a sketch in pencil, but every new position lets the software erase a wobble here, straighten a segment there, and test whether the updated line matches incoming reports. The solver keeps an eye on residuals, the tiny differences between prediction and measurement. Residuals are the lie detector of orbit work. Small and random is good. Large and systematic is the universe saying, try again. As the hours roll by, you can watch confidence bloom. The path that began as a smudge turns into a corridor, then into a ribbon. Teams generate a cloud of possible orbits that all fit the current data, then project that cloud forward to see where the object should be tomorrow, next week, next month. Those projections become ephemeриds, which are essentially travel itineraries for telescopes. Point here at this time, and you will see your quarry. The moment an ephemeris goes public, a global relay starts. Observatory after observatory picks up the baton, because nothing concentrates the mind like an object that grows fainter and farther every hour. Space agencies slide onto the stage with heavier tools. Dedicated centers run higher fidelity models that account for the gravitational nudge of planets and the gentle push of sunlight on dust. For an active comet, they watch for hints that jets of vapor are adding a tiny shove. If the numbers say those shoves are negligible, the models keep the path clean. If not, the models learn a new dance step. The agencies publish updated orbits with uncertainties that shrink like a tightening spotlight. It is not just academic glory. Accurate paths decide whether a spacecraft can take a peek, whether a radar dish has a chance, and whether the public gets a sky show or a no-show. Behind the scenes, a quiet hunt begins for recovery images, older photographs of the same patch of sky that may have caught the object by accident before anyone knew to look. Archivists and algorithms comb through years of data. When a recovery point is found, it is like discovering a childhood photo of a celebrity. The timeline stretches backward, and the orbit solution sharpens dramatically. One extra dot from months earlier can shrink tomorrow's uncertainty from a broad smear to a pencil line. It is detective work with stardust on the files. Every measurement has a personality, and not all personalities play nicely. Some telescopes run hot and need bias corrections. Some nights flirted with clouds. Analysts grade each report, reject the wobbliest ones, and resolve the orbit. It is housekeeping with consequences. Keep the messy numbers and your path will drift. Clean the list and the dots click into place. The result is typically released as a fresh set of orbital elements, along with formal uncertainties, numbers that tell you not only where the object is headed, but how sure we are about that story. The cinematic part never gets old. Imagine a wall-sized plot where each new night adds a white thread to a growing arc. You can feel the room lean forward as the arc extends, then relax as the projected corridor narrows. Someone jokes that coffee is the real propellant here. Someone else points out a quirk in the residuals and wins bragging rights by sunrise. Humor aside, the craft is patient. Measure carefully, share quickly, refine relentlessly. Space does not reward panic, it rewards rhythm. By the end of this process, the path is not a guess. It is a well-witnessed journey. The dots of light have been interviewed, the alibis checked, the timeline drawn. From a few faint hops between blinking frames, we now hold a roadmap you could plan a mission around. Our visitor's story has coordinates, and the next chapter can ask sharper questions. Speaking of which, those coordinates set up a front-row opportunity near another world, and a chance to watch a foreign snowball under red skies. Chapter 5. The Mars Flyby. A front-row science seat picture. Mars is a rust-red theater, the curtains of thin air drawn back, the stage lights set by the sun. Into this quiet hall rushes a visitor from far away, crossing the proscenium at interplanetary speed, while the balcony fills with orbiters. And the ushers, yes, the rovers, tilt their cameras up like excited fans. It is showtime on another world. The stakes are simple and delicious. Watch a traveler from beyond our star drift past the red planet and use every instrument we have there to peel clues from its glow. Earth is basically a rock that won the cosmic lottery. Mars is the open-air annex where we sometimes get a better seat. The timing is tight, and the choreography is pure space opera. As the comet makes its closest pass to Mars, far outside any danger zone, but close enough to be worth every photon, mission planners swing instruments into position. You can almost hear a conductor's baton tap the music stand. One spacecraft takes the overture, capturing broad field images to map the tail. Another steps in with the woodwinds of spectroscopy, splitting light into stripes that spell out the gases and dust grains. A third listens for the way the solar wind hisses and crackles when it meets a train of particles that did not grow up around our sun. Different sections, same symphony. Orbiters are the stars of this balcony. Camera systems with steady aim track the head of the comet against the starry backdrop, turning motion into measurements of shape and structure. High-resolution images risk a tighter crop, knowing that even a fuzzy snowball can show texture in the coma when you push exposure and timing just right. Spectrometers sniff the plume for familiar volatiles, water vapor, carbon dioxide, perhaps traces of carbon monoxide, or organics, and for any surprise that would hint at a very different freezer recipe from another system. If interstellar comets are grocery lists from someone else's kitchen, these instruments are the translators, reading each ingredient line by line. Now for the part Mars does that Earth cannot. It lets us sense the visitor through a planet's atmosphere from only one step away. The red planet's air is thin, which means less blurring and scattering. Sky-facing instruments on orbiters can look for faint meteors if dust grains from the comet intersect the upper layers, the way a few stray sparks might fall when a bonfire throws embers. Ion and neutral mass spectrometers. Mars has them, and they are very good at being nosy. Watch for any temporary changes in the exosphere, the whisper-thin envelope of atoms that hover above the planet. A spike here, a dip there, and suddenly we have evidence of how alien dust interacts with a world's breath. Enter the rovers, our ground-level correspondents. Their cameras have spent years studying clouds, dust devils, and twilight glows. For a brief window, those same eyes become comet chasers, shooting time-lapse sequences in the Martian night to catch a streak or a brightening tail. Imagine the mast of a rover angled just so, the scene framed by rocks that have not moved in ages, while overhead a visitor from a completely different neighborhood etches a pale trace. It is quietly epic, like watching a parade reflected in a puddle on an ancient street. Meanwhile, the orbiters that patrol Mars for science think long-haul prose with deep benches of instruments, run coordinated plays. One craft takes the limb view, peering sideways through the atmosphere to increase sensitivity to tenuous gases. Another points down for nadir scans, building maps of how any comet-related changes vary with latitude and local time. Radio science teams track signals passing through the atmosphere to see if electron densities wiggle as dust and sunlight shake hands. All of this happens on a clock because the comet does not slow down for anyone. Space does not do intermissions. There is a safety story here too, and it is oddly comforting. Mission teams know the history of comets paying calls on Mars. They have model runs for dust grain sizes and speeds. They understand how to orient spacecraft to minimize risk during the brief moments when the dust environment is least predictable. For this pass, the distances are friendly and the models are boring in the best way. No hazard, all science. That frees everyone to be ambitious. Point longer. Push exposure a touch. Try that new processing trick you have been saving for a clear night. Photosynthesis is plants' way of saying we invented solar panels first. Mission planning is engineers saying we invented worry first, so you can relax and enjoy the show. The beauty of a Mars flyby is the layered perspective it grants. From Earth, the comet is a distant smear. From Mars, it is a neighbor passing on the opposite sidewalk. That closeness turns subtle questions into answerable ones. How clumpy is the dust? Do jets from the nucleus flicker on short timescales? Does the interaction with the solar wind look different from what we see around comets that were born in our own backyard? If the glow changes color with time, what chemistry is writing that mood shift? Each answer becomes a calibration point for the next interstellar visitor, tightening the focus of a field that is still young. And then there is the sheer narrative elegance. A comet forged around another star glides past a planet that once had rivers and lakes, while robots built by a civilization on a third world lean back to watch. The scene compresses a lot of history into a single tableau. Frozen relic of another sun, fossil world with stories in its stones, tool-making primates who sent cameras to the right place just in time. Black holes may be the universe's way of saying delete browsing history permanently. Nights like this are the universe's way of saying remember this page. When the moment passes, the instruments power down from their peak modes. The data trickles back through the deep space network, and the long work begins. Teams will stack images, subtract stars, build light curves, and compare spectra across orbits. Tiny variations will become headlines for scientists, if not for the evening news. A slightly different ratio here, a gentler slope there, a timing offset that suggests one jet woke up before another. None of it is loud on its own. Together, it is a biography written in whispers. By sunrise on Earth, the Red Planet's theater is quiet again, but the reels are full. Our visitor has kept moving, as it always intended, on toward its brush with the sun and the far lanes beyond. Mars gave us the balcony seat, and we did not waste it. Next, we will take those frames and ask what they say about the traveler itself, its core, its sturdiness, and why this snowball seems to skip the gym only on weekends. Chapter 6. Size, shape, and that surprisingly beefy nucleus. If the coma is the rumor, the nucleus is the person who started it. Every comet looks bigger than it really is, because sunlight bounces off clouds of dust and gas that surround a much smaller core. To understand what kind of traveler we are dealing with, we have to peel away that glowing disguise and ask a blunt question: how big and how tough is the thing at the center? For 3i/Atlas, the best clues come from crisp images and clever subtraction, the astronomical version of noise-canceling headphones. Once you cancel the haze, a silhouette emerges, and that silhouette looks compact. In plain language, space, snowball, gym membership start with a challenge. The nucleus hides inside a halo that can be thousands of times wider than the core itself. Telescopes record a bright smear, and the smear is a mix of starlight, dust reflection, and a bit of gas glow. To measure the core, teams model how the coma should fade with distance from the center, then compare that to the point spread function of the telescope, the signature shape a true point of light would have. Subtract the coma model and the point spread function carefully, and you are left with whatever solid object is bright enough to stand on its own. It is finicky work. Move a knob too far, and you invent a fake pebble or delete a real one. The reward for patience is a constraint on the size. Those constraints for our visitor point away from the classic fragile snowball stereotype. The upper limits on width do not leave room for a sprawling cotton candy core. Instead, the data favor something compact, with a surface bright enough to reflect a measurable fraction of sunlight, but not so bright that it screams polished ice. Astronomers often bracket the unknown with a range of plausible reflectivities based on past comets and small bodies. Within those bookends, the allowed sizes stay modest. The surprise is not that the nucleus is small. Comet cores usually are. The surprise is how steady and well-organized the coma appears, given that small engine. That implies a nucleus with enough structural integrity to host collimated jets rather than just shedding fluff in all directions. Shape is trickier than size because the coma blurs the outline and the viewing angle keeps changing. Even so, teams look for rotation clues in the light curve. If the core is elongated, the amount of reflected light should rise and fall as it spins, a lighthouse effect written in brightness. For 3i/Atlas, the variations are not wild. That does not prove a perfect sphere. Nature rarely builds them at this scale, but it suggests either a mildly elongated body or a rotation axis, and observing geometry that softens the wiggles. Pair that with the jet behavior seen in high resolution, and a picture forms of a nucleus that is not a balsa wood toy. It has enough cohesion to spin without flying apart, to vent in persistent directions, and to keep dust production under control, even as sunlight turns the surface into a kettle. Thermal clues add texture. As the comet approaches the sun, models predict how a surface with a certain toughness and porosity should warm, crack, and breathe. If the nucleus were a loose pile of frost and talc, we would expect abrupt surges, crumbling ledges, and a storm of fragments. Instead, the production seems governed by a handful of active areas that wax and wane with solar heating and rotation, like carefully placed vents opening on cue. That points to a crust strong enough to localize activity and a sublayer that conducts heat without instantly collapsing. Dust behavior is an underrated witness. Grain sizes inferred from the brightness profile and from how sunlight pushes on those grains say a lot about the engine that launched them. A nucleus that is too weak tends to fling a blizzard of very fine particles that broaden the coma quickly. A sturdier core can loft a mixture, including larger grains that stay closer to the track and build narrow features in the tail. Observers note those narrow features, and that tips the scales toward a nucleus with real grip. This is not a sand castle collapsing under a garden hose. It is more like a pressure washer carving clean arcs from specific nozzles. All of this stacks into a narrative that surprised some researchers, not because comets cannot be tough, but because interstellar wanderers carry the extra question mark of unfamiliar origin. If the chemistry and the layering were wildly alien, one might expect brittle behavior or chaotic shedding. Instead, the core appears to play by rules that seasoned comet watchers recognize: a compact body, likely layered, with enough mechanical strength to maintain jets and keep the dust fountain from turning into confetti. That familiarity is a gift. It means the same physical instincts that served us on local comets apply here, even though the passport stamp is from another star. There is a strategic payoff to a beefier nucleus, and it goes beyond bragging rights. A compact, cohesive core is easier to track photometrically because its activity does not drown the signal in wild variability. It allows more reliable inferences about spin state from subtle, repeating patterns. It also holds out hope for catching topographic hints, gentle asymmetries in the coma that mirror cliffs, pits, or lobes on the surface. We are not resolving boulders here, but the coma can leak hints of the terrain, the way a breeze reveals the shape of a hidden sculpture. Importantly, the size limits keep mission planners realistic. If you daydream about a future probe buzzing an interstellar comet, you want a target that will not disintegrate the moment a spacecraft commits to a trajectory. The emerging picture here says the core can handle its close solar pass with something like poise. Not invincible, no comet is, but not a pushover. The term that floats around control rooms is benignly active, translated lively enough to teach us, stable enough not to ghost us mid-lesson. Step back and admire the detective work. From a luminous fog that tries its best to hide the star of the show, we extract the leading actor's height, posture, and a hint of attitude. The portrait we get is compact and capable, a traveler with a tight core and tidy habits. Space loves to throw curveballs, but this time, the curve hides a solid heart. Next, we will stop staring at the outline and start reading the ingredients list, asking what the vapor and dust actually tell us about the pantry this traveler packed before it left its home star. Chapter 7. What it is made of. Open the pantry of a comet, and you expect the classics: water, ice, carbon dioxide ice, and a spice rack of other volatiles that wake up when sunlight knocks. Our interstellar guest answers the door with exactly that vibe. No neon green ooze, no mystery alloy from the land of plot twists. Just the comfortable grocery list that makes astronomers nod like chefs, seeing flour, salt, and oil. Alien visitor, very familiar snack list. How do we know? Because light talks. When the coma puffs up around the nucleus, sunlight threads through that cloud and comes back with tiny fingerprints, Spectrographs spread that light into a rainbow and look for dips and bumps that match the ways different molecules absorb and re-emit energy. Water has a set of unmistakable patterns in the near-infrared and beyond. Carbon dioxide leaves its own calling card nearby. Even without quoting numbers or waving a chalkboard, observers can say, "Yep, that is water breathing off the surface," and "Yep, that is carbon dioxide lifting too," the way a barista can tell espresso from tea by aroma alone. The best part is how ordinary it feels. After the first two interstellar visitors, everyone wondered whether the next traveler would finally force us to add something wild to the periodic picnic basket. Instead, this one behaves like a well-mannered cousin of the comets we already know. Water is doing the heavy lifting near the sun. Carbon dioxide is punching above its weight a little farther out, as it always does, because it takes less warmth to stir it. The balance shifts as the comet approaches and recedes, and the timeline of that shift looks familiar enough to make modelers smile. Space snowball. Gym membership was the joke. Here the joke is more like space snowball, standard grocery run. That familiarity matters. It tells us the chemistry that built this object was not some bizarre one-off from a freakish disk around a chaotic star. The building blocks of icy worlds, water, and simple carbon gases seem to pop up wherever stars and dust decide to make planets. When we see those ingredients in an outsider, it is a quiet vote for the idea that planet-making follows common recipes across the galaxy. Think of it as discovering that your grandmother's bread is almost exactly like bread in another country. The technique changes, the ingredients do not. Still, ordinary does not mean boring. With careful spectra, teams tease out how much gas the comet releases as a function of time, which hints at the structure of the surface. If water and carbon dioxide rise and fall together, the layers feeding them might be mixed. If one surges while the other naps, that suggests patchy reservoirs, veins of frozen carbon dioxide tucked beneath more stubborn crusts, or sun-facing faces rich in water sources that wake fast and then settle. These rhythms turn the coma into a seismograph for a place we cannot touch. The nucleus may be small, but it has weather of a sort, driven by sunlight and rotation, with chemistry as the forecast. Dust joins the conversation with its own grammar. The color of scattered light leans reddish, neutral, or bluish, depending on the sizes and coatings of the grains. That color, together with how quickly pressure from sunlight pushes the dust outward, tells us whether the grains are more like talc, more like coffee grounds, or more like a spray of tiny pebbles. Our traveler's dust points toward a mix that comets often carry. Small grains that create a soft glow close in, blended with tougher bits that form narrow streaks downwind. Again, the headline is not weirdness. It is typicality, which in this field is priceless. We can even fish for clues about the travel history, from the way specific fragments light up. When ultraviolet photons break water into simpler pieces, a bright green cousin, short-lived in sunlight, often appears. If you see that glow pulsing with rotation or peaking at certain distances from the sun, you learn about the engine room that feeds it, carbon monoxide. Another usual suspect in comet kitchens sometimes whispers from deeper layers when the surface has crusted over. Listening for those whispers helps us rank how sealed or cracked the upper crust is, and whether this comet has been baked before. Composition is also a story of timing. Water ice sits tight until the comet warms to a comfortable threshold. Carbon dioxide gets fidgety earlier when it is still colder. If observers catch the object far out and see carbon dioxide flicker before water wakes, they can mark the moment when the torch passes from one driver to the other. That handoff is a diagnostic. It tells us not only what is present, but how it is layered and how thick the insulating skin might be. In detective terms, we are dusting the pantry for fingerprints and finding them in the order they were made. Let us not skip the emotional truth either. There is something both humbling and thrilling about learning that a rock that grew up under a different sun carries the same frozen basics we would expect from our own outer nursery. It is like meeting a traveler in a distant airport and discovering you share the same childhood snacks. The details will diverge: seasoning, preparation, local quirks, but the base flavors are familiar. That familiarity is the point. It says the physics and chemistry that knit together icy worlds are not parochial, they are portable. So yes, alien visitor, very familiar snack list. And we are not disappointed. We are relieved. Ordinary ingredients make extraordinary comparisons possible. They let us ask sharper questions later. Not what is this stuff, but how was it packed? How long has it been in the freezer? And did the chef follow a slow cold recipe or a fast freeze one? Those are age questions, wearing lab coats, and they lead naturally to the next mystery. If the pantry looks familiar, can we tell how old the kitchen is? Up next, we chase the hints that point toward the vintage of this traveler and what that might say about the neighborhood where it first learned to freeze. Chapter 8, The Age Twist, older than our solar system. If comets had family reunions, this one would show up in a vintage jacket, tell stories that start with before your star was even a sparkle, and everyone would quietly slide over a seat in respect. Grandparent energy. The clue is not a single smoking gun, but a choir of hints that all hum the same tune. This traveler likely formed long before Earth was a thing, around an ancient star from the galaxy's thick disk, and it has been on the road ever since. Start with the setting. The Milky Way is not a flat, uniform pancake. It is a layered cake with flavors that map to different eras. The thin disk is today's busy neighborhood, full of relatively young stars, swirling gas, and ongoing construction. The thick disk is the older district, where stars tend to be ancient, orbits are more tilted and puffed up, and the chemistry is a little leaner in heavy elements. Thick disk stars carry the vibe of early days, when supernovas were still figuring out the recipe book. If an icy body formed in that era, it grew in a kitchen where metals for rock and salt were in shorter supply. Temperatures were volatile, and the local traffic was rough enough to fling leftovers outward with gusto. How do we connect our visitor to that older district? Kinematics, the polite word for how it moves, is one thread. Bodies born around thin disk stars usually share the gentle swirl of our neighborhood. Their motions line up with the sun's grand tour around the galaxy. Thick disk wanderers tend to cut across that traffic with more vertical swagger and higher random speeds, like a classic car cruising diagonally through a modern roundabout. The incoming direction and cruise style of our comet fit better with the older crowd's travel habits than with the chill flow of the thin disk. It looks like someone who knows side streets the rest of us forget exist. Chemistry adds another thread. The ingredients we see, water ice, carbon dioxide ice, and other usual suspects, are not exotic, but the balance between dust and ice and the way activity ramps with sunlight suggest a nucleus that hardened under a slow, long winter. In a younger system rich in heavy elements, you would expect more rocky grit locked into the mix from the start. In an older, leaner nursery, ice grabs the stage and rock plays a smaller part. Over eons, cosmic rays and micrometeoroid taps would redden and toughen the outer layers, baking a crust that only wakes where sunlight strikes just right. That weathered but reliable behavior is the calling card of a veteran traveler. There is also the matter of timekeeping the old-fashioned way, by counting scars. We cannot see the surface directly, but the coma's behavior hints at how armored the crust is. A world that has been sun-kissed many times becomes fickle, venting in bursts and crumbling edges. A world that has drifted mostly in the cold between stars keeps a tighter lid, opening only where heat can infiltrate along cracks and seams. The steady, disciplined puffs we infer here whisper of a surface that has spent most of its life in the deep freeze, with only brief chapters of warmth. It is the energy of someone who has crossed deserts without spilling their canteen. Now picture the origin story. Long ago, around a thick disk star. A young disk of gas and dust spun itself into pebbles, then cobbles, then icy planetesimals, the building blocks of comets and small worlds. Giant planets or hefty embryos jostled the outskirts. Some bodies settled into distant, sleepy orbits. Others were evicted entirely, flung into interstellar space by gravitational shoves. Our traveler joined the exiles and began a drift through the void, so long that you could stack human history end to end, many million times, and still not fill the miles. It wandered not aimlessly, but inevitably, carried by the quiet clockwork of the galaxy. Every long road changes a traveler. In interstellar space, there is no sunlight, most days, only the slow patter of particles and the occasional jolt from a passing shockwave. Over ages, that exposure darkens surfaces, welds grains, heals weak spots, and seals pores. When such a veteran finally strolls past a star again, it does not explode into chaos at the first hint of warmth. It tests the lock, opens a vent, and lets the kitchen steam without tearing down the walls. From Earth's vantage point, that calm confidence reads as age. There is a cultural tilt here that is worth naming. We tend to assume alien means beyond our imagination, but ancient often looks familiar in a deeper way. This comet is not surprising because it is strange. It is surprising because it is textbook in a context where we expected chaos. In a galaxy that has been making icy leftovers for billions of years, ordinariness across star systems is the remarkable part. The traveler's likely thick disk birth just tells us the textbook was printed early. Age also reframes risk and reward. A robust, time-tempered nucleus is more likely to survive its brief warm-up near the sun, giving us a longer window to watch and learn. It is also more likely to carry pristine interior layers that have not been cooked to uniform blandness. Think of a geological core sample. The deeper rings hold the oldest climate notes. A crust that resists total meltdown protects those notes. If a future mission ever dreams of a passing taste, dust, not a landing, the vintage of the material would make every grain a fossil from before our own planets coalesced. And then there is the poetry of place, an object forged when the Milky Way's disk was thicker and rowdier, has swooped into our serene, thin disk suburb. And for a few months, we get to ask it questions. It does not answer in sentences. It answers in curves of light, in the timing of jets, in subtle colors at twilight distances. We translate those answers into a life story that stretches back past the sun's childhood to a crowded epoch of star birth and shoves. Grandparent energy, yes, but not frail. More like the relative who still hikes, carries their own pack, and knows which trailhead gets you to the view with nobody else around. When the visitor leaves, it will take its memories with it. What it leaves behind are ours, spectra in shared archives, light curves that students will re-examine with new tools, and a stronger sense that the galaxy's recipe book is old, sturdy, and widely shared. Next, we turn from age to fate, what gravity might have done if timing shifted, and how a giant planet could, in some alternate timeline, have tried to keep a traveler that was clearly born to roam. Chapter 9. Why the orbit looks just as predicted. There is a special thrill when an old margin note in a dusty notebook turns into front-row reality. In the 19th century, careful minds sketched a simple expectation. If a comet truly comes from beyond our solar family, it will not sign the guest book twice. It will sweep in, nod politely to the sun, and head back out. No encore. They did not have digital cameras or cloud storage, but they had clarity. Real outsiders do not loop, they breeze through. Now cut to today's control rooms with their humming servers and blinking dashboards, and watch 3i/Atlas perform the exact move the elders anticipated. It is the scientific equivalent of a call and response across centuries. The call, a true drifter, should look almost straight through. The response, copy that, performing now. Why did those earlier thinkers land on this idea in the first place? They were students of gravity and pattern. They had watched the regulars, the comets that leave for years or centuries, but return like seasonal birds. Those regulars travel on closed paths, graceful ovals that loop them back eventually. But a traveler from far beyond the sun's pull would not be trapped in that way. The simplest, safest starting picture for such a passerby was an open curve that never closes, seen over the short window available to 19th century observers. That open curve would masquerade as a near straight shot that bends only near its closest brush with sunlight. In plain terms, if it is not from here, it will not act like it lives here. Fast forward to this century and replace chalk dust with gigabytes. Survey telescopes sweep enormous swaths of sky, compiling night after night of precise positions. Orbit solvers, those quiet virtuosos of modern astronomy, string the dots together and ask what shape best explains the motion. For 3I/Atlas, the line that fits is exactly the line the 19th century playbook told us to expect, an open track that bends and then continues on its way. No looping arc waits off stage. There is no secret second act where our traveler turns around and comes back for another curtain call. When the math is stripped to its bones, the orbit is the very image of thanks for the sunlight. See you never. Earth may be a rock that won the cosmic lottery, but sometimes the prize is simply getting to watch good predictions age well. The beauty is in the continuity of method. The elders started from first principles and limited data. We start from the same principles and lavish data. They approximated with the borderline case that sits on the fence between bound and free. We turn the crank with more checkpoints and shrink the uncertainty until the openness of the path is unmistakable. Different tools, same backbone. It is a reminder that progress often looks less like throwing out old maps and more like adding detail to them until the coastline sharpens. There is also a cultural echo. In that earlier era, astronomers were moving comets from the realm of omen to the realm of itinerary. They wrote down positions, compared notes, and argued carefully over shapes that best captured the motion. Today, we do the same thing at scale and speed, but the manners have not changed. You still start with a sober guess. You still let new nights weigh in. You still resist the urge to embroider the unknown. Science loves new toys, but it loves honesty even more. So why is the match between expectation and reality so satisfying? Because the temptation with anything labeled interstellar is to expect wildness. We brace for erratic zigs and inexplicable zags. But the universe can be surprisingly literal. A visitor from away behaves like a visitor from away. It arrives carrying the extra energy that freedom demands, and the sun's gravity bends it without catching it. The path is elegant, not chaotic. It is the quiet, competent move of a traveler who knows exactly how to find the exit. This neat fit between prediction and performance gives us permission to be bolder in our questions. If the broad arc is so well behaved, then small deviations become louder clues. Subtle shifts in timing as the object warms, tiny nudges from outgassing, faint changes in the brightness of the coma. These become the whispers worth straining to hear. The big picture is already painted. Now we can focus on brushstrokes. That is the best kind of progress, when a framework is strong enough to let the details carry the drama. The match also protects us from bad storytelling. When an interstellar object acts just as the textbooks expect, it undercuts the siren song of conspiracy theories and the reflex to turn every sky streak into a cosmic cliffhanger. The truth here is plenty cinematic on its own. A body forged around another sun strolls through our daylight and continues into darkness. No special effects needed. The elegance is the point. Photosynthesis might be plants saying they invented solar panels first. This orbit is celestial mechanics, saying it wrote the user manual before we were taking notes. There is a practical payoff too. Predictability makes coordination possible. Knowing the path behaves the way a true outsider's path should, lets mission teams plan exposures to the minute and schedule instruments like a relay. It means ephemerides Stay honest, and telescopes do not flail around chasing phantoms. The old reasoning does not just make us feel good, it saves precious time while a fast-moving target is still bright enough to interrogate. And then there is the human factor. It is deeply reassuring to watch a clean idea cross generations intact. A scholar in a lamplit study reasons out what an outsider's arc should look like. Centuries later, people at consoles gather that arc in fine detail and nod. It is a handshake across time. Not every scientific story ends this way. Many old ideas deserve retirement, but when an enduring insight meets fresh evidence and both smile, you get that rare moment where the past and the present share a table and order the same thing: alien visitor, familiar geometry. By the time 3I/Atlas recedes, the phrase "just as predicted" will have grown comfortable, not complacent. It means we can spend less energy proving the broad outline and more energy mining the little deviations for secrets. Which brings us to a delicious possibility the elders also knew to consider. What if the universe had tilted the timing just enough for a giant planet to take a shot at capture? What sort of unlikely dance would it take for Jupiter to put a hand on the shoulder of a traveler that clearly prefers the open road? Chapter 10. What if Jupiter tried to keep it? Imagine Jupiter in a velvet jacket at the door of the solar system's hottest club, flashing that stormy red eye like a bouncer who has seen it all. Big gravity, bigger attitude. Now picture our interstellar traveler striding past with a cool "I am just browsing." Could the giant lean in, lower its voice, and say, "Stay a while"? Gravity is persuasive, but capture is rare. Jupiter is a cosmic bouncer with a very selective guest list. Here is the core of the problem in plain language. To keep a drifter, you must steal enough of its freedom that it stops being a visitor and becomes a regular. In space talk, the traveler must lose energy relative to the sun so that its path changes from open road to closed loop. The sun runs the venue. Jupiter is only the head of security. A single flyby can bend a path, even bend it a lot. But unless something drains energy at just the right moment, the guest still leaves after a dramatic twirl. It is the difference between a nudge toward the dance floor and actually getting someone to stay for the late set. There are a few routes to true capture, and all of them rely on exquisite timing. The most famous is the gravity assist that both speeds and slows depending on direction. If the comet arrives in a way that it passes ahead of Jupiter in Jupiter's orbit, the planet's pull can act like a hand on the shoulder that slows the comet with respect to the sun. Pass behind, and the same pull becomes a push that speeds it up. For a free spirit from another star, the window where a head lines up perfectly, the distance is just right, and the curvature of the track cooperates is painfully thin. Miss by a little, and you get a bent exit. Hit it dead on, and you might convert the comet's open path into a wild, stretched loop that still counts as a win for Team Jupiter. But even that magical geometry often only buys a temporary membership. The new loop may just be a long, shaky detour that leads to a later ejection. The solar system is a pinball table, and Jupiter is the big bumper. A captured object can rattle around, cross paths with the giant again, and get kicked back out on a future night. Astronomers call these brief stints temporary capture, which feels poetic and just a bit tragic, like a traveler who tried settling down, then remembered the road. So what makes a permanent stay more likely? Two-step dances help. One classic path is to arrive not alone, but as a pair. If our traveler were a loose binary, two chunks circling each other, Jupiter could tear the pair apart in a close pass. One chunk would leave with extra energy, the other with less. If the less energetic partner loses enough, it can slip into a bound path around the sun, perhaps even as a new member of the short-period comet crowd that Jupiter so often manages. The price of admission is sacrifice. One partner speeds away richer, the other stays poorer and bound. Cosmic finance, but with ice and rock. Dissipation is another ally of capture, though nature does not offer much of it in deep space. air drag does the trick for satellites around Earth, because the atmosphere skims a little energy every lap. Jupiter's atmosphere could in principle do that too, but dipping a fragile comet low enough to feel drag is like trying to give a marshmallow a suntan with a flamethrower. More likely than gentle braking is a breakup. That did happen to a famous comet that ventured too close, but its fate shows the risk. The price of braking was becoming a string of pearls, and then confetti. Capture, yes. Long-term companionship, not so much. There is also the subtle possibility of resonant shepherding. If a comet's new loop after an initial flyby happens to line up with Jupiter's year in a tidy ratio, repeated tugs at the same spots can gradually reshape the path. Think of a child pumping a swing at the right rhythm over dozens or hundreds of swings. The arc grows or shrinks. For a drifter from another star, you would need the first pass to set up a rhythm so precise that later passes keep adding the same kind of nudge. The universe can do this, but it is picky. Even small shifts from other planets or from the comet's own jets of gas can throw the metronome off. What about the spots where Jupiter already keeps long-term company? The clumps of asteroids around the Lagrange points that lead and follow the planet like honored escorts. Could a newcomer be parked there? In theory, a slow enough object could drift into those gravitational eddies and swirl. In practice, an interstellar comet tears through the neighborhood with a traveler's stride, not a stroller's amble. Catching one in the eddy would require it to arrive almost matching Jupiter's pace and heading like two cars merging side by side without touching brakes. That is not impossible, but it is the definition of you had to be there. At that moment, in that lane. Let us imagine the what-if victory anyway. Suppose the timing was chef's kiss, and Jupiter managed a Goldilocks pass. The comet would switch to a stretched, looping path that dips inside the giant's orbit and then swings far out. A new recruit to the short-period family. Its name would earn a footnote, born under another sun, domesticated by the big planet's pull. Scientists would throw parties, in a data processing kind of way. We would suddenly have a long-term laboratory to study an interstellar body on repeat visits, comparing how it changes season by season. The webcams would warm up, the models would sharpen, the jokes would write themselves. But reality is stingier. Most visitors fly by too fast and too off-angle for the exact handshake required. Jupiter bends them, sometimes spectacularly, and sends them on with a story to tell. Capture remains the exception, not the rule. The cosmic bouncer nods respectfully as the guest leaves and goes back to monitoring the line. The door is always open. The velvet rope almost never lifts. Speculation is delicious when it teaches, and this one teaches humility. Gravity is mighty, but choreography is king. Without perfect timing, even a planet that could swallow 1,000 Earths cannot hold a pebble that prefers the open road. Next, we will turn the lens from big planet what-ifs to the fragility question. If a traveler like this skimmed closer to the sun, could it crack or crumble? And what secrets would a breakup spill across the sky? Chapter 11. What if it broke apart near the sun? Imagine our traveler leaning too close to the campfire. The surface hisses, pockets of gas pop like dumplings, and stress lines sneak through the crust. Most comets handle the heat with dramatic flair and then move on, smoky and proud. Some, though, cross an invisible line and come apart like a stale cookie. If that happened to this interstellar guest, it would not be a failure of the story. It would be a sudden flood of footnotes. Breakup is nature's forced confessional, and astronomers love a confessional. First, the signs. Before fragments appear in pictures, the light curve tattles. A comet that is holding together tends to brighten and fade in a smooth arc as it approaches and leaves the sun. A comet that is losing its grip often surges brighter in a jagged step, like someone turning up a dimmer switch in jumps rather than a glide. Then the brightness stalls, or even drops, while geometry still says it should climb. That mismatch is a red flag. The nucleus may have cracked, exposing fresh ice that flares and then bleeds out. Soon after, the shape gives the game away. A healthy comet shows a tidy coma and a tail that flows like a windsock. A stressed one starts sprouting lumps, with the central glow splitting into multiple peaks. Stack images night after night, and those peaks drift apart at walking speed on a planetary map, but highway speed in space. The tail becomes striated, with new streaks that mark where chunks shed dust on separate schedules. If you overplot those streaks with models of dust released at different times, the picture that fits looks less like a single fountain and more like a row of leaky hydrants. Chemistry changes too. Spectrographs that had seen a steady ratio of water to carbon dioxide may record sudden swings, as if a sealed pantry door blew open and new shelves rushed into view. If a layer rich in more volatile ices fractures, the vapor mix tilts for a while toward the easier evaporators, then drifts back as the debris cloud settles. The timing of that swing, and how long it lasts, tells you how deep the crack ran, and whether the comet's interior is a homogeneous slush or a layer cake of different ices and dust. Spin is the drama beneath the drama. Comets vent unevenly, and uneven vents push. Over days to weeks, those little pushes can spin a nucleus faster, like a skater pulling in their arms. A body with internal strength shrugs and keeps twirling. A fragile pile of blocks hits a rotation rate where the seams unzip. If breakup happens, careful monitoring of fragment spacing can back out the moment the spin crossed the line. That gives a handle on tensile strength, a down-to-earth phrase for how well the material resists being pulled apart. The answer helps sort just the age-old comet personality test: solid heart or rubble pile wearing a snowcoat. Heat is the other actor, and it is sneaky. Sunlight does not warm a nucleus evenly. No? One face bakes while the night side chills. Then rotation flips the situation. The daily stress from that cycle runs along existing pores and voids, turning hairline cracks into fault lines. The depth that heat can reach in a day is called the skin depth, and it depends on how tightly packed the grains are and how well they conduct warmth. If breakup begins at a depth consistent with a thin skin, you are seeing a brittle crust failing. If the failure looks deeper, you have evidence for conduits that carry heat inward, or for layers with different thermal personalities stacked like sheets in a messy closet. Not all breakups are thermal. Tides can do the job if a comet swings near a massive body. The famous string of pearls that once grazed a giant planet is the poster child here. In a close solar pass, tides are weaker than raw heating for most comets. But if the approach distance shrank enough, the sun's gravity could still help a stressed nucleus part along its weak planes. Comparing the spacing and sizes of fragments to what tidal models predict helps decide which culprit did more work: heat, spin, or pull. Dust is a gossip who never sleeps. When a comet sheds fragments, the size distribution of dust grains often shifts toward larger clumps because boulders break and loft pebbles, not only powder. Telescopes can read that shift from how the tail scatters sunlight at different angles. A sudden tilt toward chunkier grains says the breakup reached cohesive material rather than just skimming frost. Polarization, the way light waves line up after bouncing off dust, changes too. That change fingerprints surface texture and porosity. In other words, even the sparkle of the dust cloud carries news about the grit in the walls of the ancient ice. Now, what would astronomers do the minute they sensed a crack? They would push cadence. Nightly images would become hourly. Teams would coordinate to watch in different colors and at different times of day, catching rotation effects and chemistry swings. High-resolution instruments would try to resolve fragments individually, track their paths, and see whether they continue to vent or go dark. If one fragment brightened on a different rhythm, that would suggest it exposes a distinct vein of volatiles or has a different spin. Each shard becomes a probe of a different slice through the parent body. The value of all this is not only a good story, it is a blueprint of how ancient ice is built. Breakup reveals whether the nucleus is laminated like pastry, granular like a snowbank, or knotted like a compressed tumble of pebbles. It tests how gas carves channels and how dust locks together. It lets us compare an interstellar fossil to local cousins that have crumbled before. Some nearby comets fell apart in a rush near the sun and left a long, soft debris train. Others cracked earlier and drifted into invisibility as their fragments faded. Placing our traveler on that spectrum would say whether time in interstellar space tends to weld or to weaken, to heal pores or to seed fissures that wait patiently for a warm day. There is risk, of course, that a dramatic breakup spoils later chapters. Fragments fade quickly, and the window for rich data can slam shut. But even a brief storm leaves fingerprints in the tail that linger for weeks, curling and spreading like smoke rings. Those rings can be modeled backward to reconstruct the moment of failure, a sort of comet forensics that is less loud than fireworks and more instructive than any single snapshot. If the traveler keeps its cool, we learn from restraint. If it fractures, we learn from honesty. Either way, the sun makes sure the lab practical is graded. Up next, we will deal with the human side of sky drama, how to separate the real science from the doomer headlines, and why a busy comet in the news does not mean you need to unplug your toaster or move the couch. Chapter 12, Debunking the Doomer Memes. Open the group chat, and you will find at least one message that reads like a movie trailer. Ominous music, grainy sky photo, and a caption that basically says, "Brace for impact, deep breath." We are going to do this the calm way. Your toaster is safe, your couch can stay where it is, and the cat does not need a helmet. Space drama, zero household risk. First principle, distance is destiny. Things in the sky can look close because the canvas is flat to our eyes. But orbital reality is three-dimensional and big enough to make road trip metaphors feel tiny. A visitor on a flyby that never comes near Earth's lane is like a plane cruising at high altitude while you are parked on a quiet street. You can hear it, you can point at it, but it is not landing on your roof. When astronomers say there is no threat, they are not guessing. They have a timetable and a map that says the closest approach stays far outside the neighborhood. In Sky Talk, far usually means more room than you would need to fit many Earths lined up between us and the object. That is not a near miss. That is a polite wave from across town. Second principle, risk is not a vibe. There is a whole playbook used by planetary defense folks whose job is to worry so you do not have to. It starts with a corridor of possible paths, then trims that corridor as more observations roll in. If any sliver of that corridor ever crossed Earth, even years from now, the object would get flagged and moved to a watch list with a name that sounds like a superhero task force. You would see sober updates, not rumor threads. For this visitor, the corridor never gets anywhere near our spot. The math has spoken, and it says enjoy the show, then back to regular programming. Third principle, size and speed matter, but context matters more. Small objects zip by all the time and burn up in the upper air as pretty streaks. Bigger ones are rare events, and the world has a catalogue of the usual suspects that could pass closer in some year we can name. That catalogue is why you sometimes read about harmless flybys. Those are the known neighbors doing known loops. An interstellar traveler on a one-time pass that stays well out of range is not a secret boss level. It is a tourist on the express lane. Batuta, so where do the apocalyptic posts come from? One source is simple confusion between brightness and bigness. Comets can look dramatic because sunlight catches their dust and gas, making them fluffy and photogenic. Fluffy does not equal heavy. A streetlight looks huge in fog. It is not going to fall on you because the glow got wider. Another source is the mashup of words like close and approach with pictures that imply scraping past the atmosphere. In astronomy, close might still be farther than the distance between the sun and the far side of the planet at noon. That is close the way a mountain is close when you can see it from a clear valley. Pretty, not perilous. There is also the classic plot twist. Someone posts a graph with a lot of lines and a scary arrow, then declares doom in all caps. Those lines usually show where telescopes around the world are pointing, or they show the planned path through empty space, not a collision course. Imagine confusing a train timetable with a car crash report. Timetables look busy. They are not warnings, they are schedules. Curves on a sky plot do not mean a bullseye. They mean this is how we know where to look. If you want a no-nonsense way to sanity check a claim, try this. Ask where the numbers came from and whether they include uncertainty. Real updates from observatories. Mention when and how a measurement was made, and how sure they are about it. Viral memes never include uncertainty because it ruins the vibe. Real updates also change with new data, and they say so. That is not flip-flopping, that is refinement. The sky rewards people who keep sharpening their pencils. Here is a comforting truth about our species. We have built a global early warning system because we are very attached to staying unbonked by space rocks. Arrays scan the sky every clear night. Automated software catches motion. Professionals and amateurs cross-check. When something interesting appears, it gets tracked hard. If there were an impact scenario, you would not first hear about it from a yelling video with spooky music. You would see coordinated, measured statements. It would feel like a weather alert, not a cliffhanger. But wait, does a far pass at least shake loose storms or earthquakes? No, comets do not control your mood, your soup, or your tectonic plates. The tides you feel are set by the moon and the sun, which are steady and predictable partners in this dance. A distant, fast visitor does not have the time or the reach to tug oceans or trigger fault lines. It does not change the radio signal in your car. It does not make pets bark. If your dog is barking, your dog is just being a dog. So how should you enjoy the moment, minus the fear filter? Treat it like a limited time art show. Some nights may offer a faint fuzz in binoculars. Some mornings, a subtle tail, if you are under a dark sky. Even if you never see it directly, the idea itself is a gift. A fragment of another star's nursery is passing through our sunlight, and teams around the world are turning that pass into knowledge. That is the opposite of a doomer story. That is a curiosity dividend paying out. A good rule for the next space headline: pair excitement with patience and jokes with facts. Laugh at the overblown captions, then check the actual trackers. Space loves a spectacle. Science loves clarity. In this case, clarity says the visitor stays far away and keeps going. You can keep the couch where it is. You can keep the toaster plugged in. Space drama, zero household risk. Next, we will pivot from public perception to the physics of subtle forces, and why this traveler's motion is remarkably clean. No mysterious swerves, no secret handbrake turns, just the quiet confidence of a body letting gravity do the driving. Chapter 13. Why no weird rocketing or zigzags? If you've ever watched dashcam compilations, you know the feeling when a perfectly calm road turns into a carnival of sudden swerves. Space has its versions of those clips. Some comets do odd things. Their brightness jumps, their path shifts a hair, and analysts squint at the plot, asking, did the driver yank the wheel? Those detours usually come from non-gravitational forces, gentle but persistent pushes from jets of vaporized ice, acting like invisible thrusters. Our interstellar guest, though, has been gliding along like it took a defensive driving course from the cosmos. No space handbrake turns. Let us take a step back. Gravity is the main choreographer. Left alone, a comet follows the smooth curve set by the sun and the planets, a quiet ballet with predictable arcs. But comets are not rocks carved from stubborn granite. They are freezers with leaky valves. Sunlight warms the surface, ices sublimate, and gases stream away from vents. Every puff carries momentum. If a vent happens to point in a persistent direction, the nucleus gets a tiny nudge in the opposite direction, the way a garden hose wriggles in your hands when the water hits the air. Add up many hours of that hose pointing roughly the same way, and the path can wander off the purely gravitational chalk line. Astronomers watch for these little shoves by comparing prediction to reality over many nights. The orbit solver draws a best fit track from all the measurements so far, then predicts where the comet should be later. If later arrives and the comet is consistently a smidge off to one side, that is a hint that gas jets are adding their 2 cents. When the offsets are tiny, random, and cancel out, you blame measurement noise. When they are steady in one direction, you whisper non-gravitational. The trick is that telescopes are really good now. We can sense offsets that would have been swallowed by noise a generation ago, which makes the verdict here more impressive. Even with sensitive eyes, we are not seeing strange accelerations. The path looks clean. Why might this particular traveler be so well behaved? Start with balance. If active areas are sprinkled around the surface in a way that averages their pushes over a full spin, the net shove is close to zero. Picture a chef spinning while holding 4 kettles that vent steam. If the kettles are placed evenly, the spin is steady. If one kettle dominates on one side, you get a wobble. Our comet seems to be running the even kettle routine. Plenty of activity, but spread out so the pushes cancel. That makes the path hug the gravity line with satisfying stubbornness. Spin state matters too. If the nucleus rotates in a stable, not chaotic way, think steady top, not a wobbling toddler toy, then any individual jet's push points in different directions as the face turns from night to day. Over one full rotation, the pushes smear around the compass and add up to almost nothing. A chaotic spin can lock a vent into a lopsided schedule that favors one direction. Nothing here screams chaos. The brightness variations hint at regularity, a metronome rather than a drum solo. Regular spins make for tidy trajectories. Surface texture adds another quiet guardrail. A crust with small, well-sealed apertures tends to produce narrow jets that switch on and off with the sun. Those jets are dramatic in photos, but average out quickly. A ragged, heavily fractured surface can act like a broad exhaust, pushing in a single orientation for long stretches. Our traveler's behavior suggests the former, vents that wake and sleep briskly, distributing the momentum budget rather than letting one region bully the path. You might ask, what about the big pressure waves from the solar wind or the steady pressure of sunlight itself on dust? Sunlight does push on small grains, shaping the tail, but the nucleus is many orders of magnitude heavier than any individual fleck. The net effect on the core is tiny compared to the clean pull of gravity. The solar wind rattles the coma, but does not grab the nucleus by the collar. So unless the nucleus itself becomes a spray can of gas for long, sustained periods, those environmental nudges stay in the background. There is a philosophical sweetness to a clean orbit. It lets us draw a crisp baseline. When the trajectory behaves, we can confidently attribute any subtle deviation in brightness to changes in activity and not to hidden steering. That, in turn, tightens the inferences we make about the nucleus, its spin, its heater and thermostat routine, its crust. If the car is staying in its lane, you can listen for engine noises without worrying the driver is swerving to avoid raccoons. The absence of weirdness also keeps the rumor mill from grinding. When a comet's track suddenly jogs sideways, the internet invents explanations faster than you can say Occam's broom. Thrusters, alien intent, secret forces, name your spice. A well-behaved path is a gift to clarity. It says the gravity we understand is doing the heavy lifting, and the comet is content to let it. Boring can be beautiful. In fact, boring is how you know you can trust the rest of the story. None of this means the object is inert. It is venting, it is growing and shedding a tail. It is changing its look with sunlight, but its internal plumbing is tuned in a way that keeps thrust impulses small and symmetric over time. Imagine a marathon runner who breathes evenly instead of gasping. The motion forward is all lungs and legs, not flailing arms. Our comet is that runner, working hard, not wandering. Could that change later? Certainly, as the sun warms different seams, a new vent could open that favors one direction for a while, and the orbit models would adjust to include a gentle non-gravitational turn. If that happens, you will not see a skid mark. You will see a graceful, slightly new curve that still respects the dance floor. For now, the score reads gravity 1000, jets 0, no space handbrake turns. This is the kind of under-the-hood result that makes the next chapters easier. With a trajectory steady, we can plan observations with sharp timing, catch repeating patterns tied to rotation, and stack data from many nights into high-confidence portraits. The road is straight, the signals are clean, and the driver is calm. Next, we will open the toolbox on how telescopes pass that clean light, how instruments split rainbows into recipes and turn a faint smear into a chemistry lesson worthy of a backstage pass. Chapter 14, How Telescopes Turn Light into Clues. If the comet's glow is a song, telescopes are the studio gear that splits the track into vocals, bass, and the tiny shaker you never noticed. The trick is spectroscopy. Take white light, stretch it into a rainbow, then read the faint barcodes hidden inside. Each dip or spike is a molecule clearing its throat. Water hums in one part of the rainbow, carbon dioxide sways in another. Dust adds a soft, hazy harmony across the whole thing. Spectroscopy is basically turning rainbows into receipts, and the receipts say what is in the cart. Start with a simple picture. A regular camera gives you brightness. The comet is this bright tonight. A spectrograph gives you story. The comet brightened because this gas woke up and that dust thickened. The instrument works like a prism with ambition. Light from the fuzzy head is fed through a slit. Imagine a tiny mail slot, so only a thin slice of the coma is sampled. A grating stretches that slice into a spectrum, and a sensitive detector records the pattern. Back in the control room, someone looks at a squiggly line and grins, because a small wiggle at a very specific color means a specific molecule just raised its hand. Temperature sneaks in through the same door. Molecules glow differently at different levels of warmth, and the balance between lines acts like a thermometer. You do not see a number on the comet's forehead. You read the thermostat from how high each note sings in the spectrum. Dust temperature is caught another way. At longer wavelengths, warm grains whisper in thermal light. When a telescope that sees in the mid-infrared listens, those grains confess how toasty the coma has become. Dust is a gossip. Give it the right wavelength, and it spills everything. Now picture the band. No one observatory can play every part well, so campaigns turn into collaborations. A big optical telescope with a high-resolution spectrograph is the lead guitar, teasing out narrow features that separate water's glow from a neighbor's. A space telescope sensitive to infrared is the vocalist, strong on the warm dust and the quiet gases that only sing in heat. A millimeter array acts like the bass, mapping heavy, cold molecules across the coma and tail and showing where gas is pooling or streaming. A small robotic telescope becomes the drummer, keeping the beat with nightly light curves that say whether the whole comet is in a rising or settling mood. When the band is tight, you hear the song, not the instruments. Coordination is a craft. Teams circulate ephemeриdes, the treasure maps that say point here at this time. They block out windows where one telescope hands off to another so that coverage overlaps, like relay runners meeting in stride. Calibration stars, the choir of well-behaved lights we use to check instruments, get observed before and after the comet, so we can scrub out Earth's own atmospheric fingerprints. On a good night, 3 observatories on different continents are watching the same jet flicker and comparing notes by sunrise. On a great night, a space observatory above the air joins in, and the mix goes from studio to live album. Polarimetry adds spice. Instead of how much light, it asks how the light is lined up. Dust scatters sunlight with a preferred orientation. By measuring that alignment, you learn grain sizes and surface textures. It is like reading footprints to decide whether a beach is made of fine sand or crunchy shells. When the alignment changes with distance from the nucleus, you know the dust grain recipe is evolving as particles collide, clump, and drift. Integral field spectrographs are the modern multi-tool. They take a small, two-dimensional view and record a spectrum at every point, building a little cube of data. 2 axes for position, 1 for color. Slice the cube one way, and you get a map of water. Slice another, and you get a map of dust. Compare the maps, and you see whether gas fountains line up with dust plumes, or if they are offset like stage lights and smoke machines that were set by different crews. If you ever wanted to know whether the left side of the comet's head is in a different mood than the right side at dawn, this is your toy. Not every clue lives in fancy hardware. Time is an instrument too. By repeating the same measurements night after night, you catch rhythm, a gentle pulse at the rotation period, a slower swell as the comet moves into stronger sunlight, a drop when a jet goes dormant. Stack spectra by phase, where in the spin you caught the comet, and you can reconstruct which vents face the sun, at which times, and how quickly they answer the call. It is choreography learned from light. And yes, you can overdo it. With so many instruments and so many wavelengths, the danger is turning the song into noise. That is where thoughtful modeling steps in. Simple physical models, how jets expand, how dust drifts, how sunlight falls across a turning surface, act like sheet music that keeps the band together. If the model says the waterline should rise 2 beats after dawn on the nucleus, and the infrared dust glow should lag by 1 more beat, and the data do that dance, you have a tune you can trust. There is a human part to this band, and it looks the same in every control room. Sticky notes on monitors, a shared spreadsheet open on one screen, a chat window full of timestamps and short cheers. Someone pulls an all-nighter to catch a window when the comet clears the horizon for 15 perfect minutes. Someone else writes the code that aligns the spectra and subtracts the sky with the grace of a magician palming a coin. The payoff is not just a pretty plot. It is the moment when the lines lock in and a physical picture clicks. Gases waking along a ridge, dust thickening along a valley, a nucleus running a tidy day-night routine like a tiny, ancient town. Spectroscopy turns faint smudges into sentences. Multi-observatory teamwork turns sentences into chapters. And when a visitor from beyond our star gives us a few weeks of clear skies, the band plays until the lights come up. Next, we will address the question that always lurks at the edge of curiosity. Are we being pinged? And how do we responsibly separate a fun thought experiment from the overwhelmingly natural song this comet is singing? Chapter 15, The Are We Being Pinged? Detour. There is a moment in every sky story when someone leans in and whispers, "What if it is not a rock?" The whisper travels faster than photons and picks up special effects along the way. Suddenly, the comet's tail is a trail, the jets are engines, and the light curve is a message that only needs the right decoder ring. Science hears the whisper. Science also checks the batteries in the flashlight before running into the basement. In other words, curious, not credulous. Extraordinary claims need more than a spicy headline. Let us set the table. A technological artifact would leave fingerprints that do not look like geology or ice behaving under sunlight. You would expect geometry that resists dust and gas explanations, signals that repeat with crisp engineered timing, or material properties that shrug off the usual thermal dance. Instead, what we actually see from this traveler is the greatest hits of natural behavior. The glow brightens predictably as it moves into stronger sunlight. The gas species line up with temperatures that wake them in the correct order, and the tail points exactly where solar pressure says it should. That is not the vibe of a machine. That is the vibe of a freezer, though politely under a heat lamp. Take variability. Natural objects are messy, in a charming way. Their brightness wobbles because the nucleus rotates and different vents face the sun. Those wobbles are not metronome perfect. They drift as day-night boundaries shift across rough terrain. A beacon, by contrast, would advertise regularity. If you want to be noticed across interstellar space, you do not pick a rhythm that meanders. You pick a pulse that a bored grad student can recover after a bad night's sleep. Here, the changes look like sunlight plus topography, not a drummer with a click track. Consider spectra, the rainbows turned into receipts. Our visitors' receipts are the grocery list of a comet: water, carbon dioxide, and dust that scatters light with the textures we expect from grains lofted by vapor. It is exactly the set you get from a compact nucleus, with active areas that heat, breathe, and rest. A constructed object would have to do an elaborate impression of comet chemistry, including the way ratios evolve as distance from the sun changes. That is a lot of cosplay for an advanced civilization. If the plan were to get our attention, there are shorter routes than pretending to be snow. Shape and motion tell the same story. The path through the solar system matches the quiet arithmetic of gravity, with no surprise accelerations, no sudden course corrections, and no long burns that would leave a detectable signature in the orbit fit. The coma's outline changes in ways that match a spinning, irregular body being warmed unevenly, not a craft slewing to keep an antenna aimed. If there is a pilot, they are committed to method acting. Now, about the whisper itself. It thrives because the unknown has edges, and edges invite folklore. The right way to visit those edges is to carry a set of questions that could flip the story if the universe answered yes. Do we see narrowband radio or optical tones that repeat on human-friendly timescales? Do we see polarized light signatures that match manufactured surfaces instead of dust grains? Do we detect accelerations that persist in one direction, unrelated to sunlight, rotation, or gas flows? Those are falsifiable tests. Thus far, the answers behave like nature, not like engineering. The media ecosystem does not help. Somewhere between a careful preprint and your cousin's social feed, nuance can be replaced with sizzle. A headline that says unusual object exhibits properties consistent with volatile outgassing becomes mystery visitor, defies physics. Physics is not being defied. Physics is humming along, politely requesting more observing time. When a claim leaps straight from eyebrow raise to exclamation point, it is a good time to ask, who is making the claim? What did they measure? And what would make them change their minds? Science loves an anomaly, but it loves a reversible story even more. There is also the history lesson. We have been here before, with objects that briefly wore the maybe engineered cloak, only to reveal a natural lining after better data. The pattern is not one of disappointment, it is one of sharpening vision. Every time we build a clearer instrument or model, a messy process more honestly, the weird becomes ordinary in a more interesting way. A world getting good at distinguishing the unusual from the unreal is a world doing science right. None of this means we close the door on wonder. Quite the opposite. We keep the door open a crack and wedge it with measurements. If any observation starts to sing off-key, an energy distribution that refuses all thermal explanations, a timing pattern so rigid it looks like a clock, a material reflectance that screams polished alloy rather than weathered dust, then the conversation shifts. The bar for engineered is not infinite. It is just higher than a gust of gas and a photogenic tail. Maybe the best metaphor is a detective show. The audience wants a twist. The detective wants evidence that survives the next scene. Right now, the case file is full of fingerprints that match comets we have known. The way jets turn on, the way dust drifts, the way light scatters off grains with familiar sizes. The twist would require a print that does not belong to anyone in the usual database. We have not found that print. We are not mad about it. We are busy enjoying how much a natural object can teach when you stop trying to make it confess to a crime it did not commit. So yes, entertain the thought experiment. Ask the interesting questions, build the tests that would let us know, unambiguously, if a traveler ever arrived wearing more than ice. But let the current traveler be what the evidence says it is, a well-behaved comet from another sun, writing its biography in sunlight and vapor. The sky is generous enough that we do not need to force it into science fiction for it to feel like magic. Next, we pivot from the detective's office to the street outside, where the public can actually join the watch. How amateurs, students, and backyard telescopes help extend the record, and how a global network turns curiosity into data you can hold in your hands. Chapter 16, Citizen Science. How viewers can follow along. Picture a porch at dusk, a mug warming your hands, and a patch of sky that is just getting its first stars. Somewhere in that growing darkness, our interstellar traveler is sketching a path you can actually catch if you know where and when to look. You do not need a mountaintop observatory or a lab coat. You need curiosity, a plan, and a few tools that the internet and a friendly neighborhood telescope shop can help you find. Backyard telescopes, global science, start with the playbill updates. Professional teams publish predicted positions called ephemerides, but you do not have to translate arcane tables by lantern light. Modern sky apps and planetarium programs digest those numbers and serve them up as simple maps. Type the comet's name, spoken out loud as 3i/Atlas, and you will get a finder chart for your location and date. The chart looks like a treasure map, where X marks where the fuzzy treasure will drift hour by hour. Print it or take a screenshot, and you are halfway to your first sighting. Next up, gear check. Your eyes alone may catch the faint smudge under very dark skies, but binoculars are the true gateway drug of stargazing. Something in the 8x40 range or 10x50, braced on a lawn chair or a tripod, will turn a maybe into a yes. A small telescope in the 4 to 6 inch class is the sweet spot for many backyards. You do not need a spaceship on legs. You need steady optics and a finder scope that stays aligned. Add a low-power eyepiece to take in the whole coma and a medium one to tease out structure. Comets are like campfires. The wide view shows the glow. The closer view shows the sparks. Find out whether your sky is a friend tonight. The moon is a romantic, but it washes out faint comets like a diva hogging the spotlight. Aim for nights when the moon is small or below the horizon during your planned watch. Check your local weather for transparency and steadiness. Humidity and haze turn comets into rumors. If you can pick out the Milky Way as a pale river, you are in business. If you can only see the 5 brightest stars, treat the night as a rehearsal and go for the vibe rather than the data. When you are ready, do what astronomers have always done. Make a plan and keep a log. Jot down the date and time, your location, the instrument you used, and what you saw. If you can estimate brightness by comparing the comet to nearby stars of known magnitude, you are contributing a classic measurement that helps professionals track activity in real time. If that sounds fancy, do not worry. Many citizen science portals include step-by-step guides that teach you how to do it with practice charts. After 2 or 3 sessions, you will be calling brightness to the nearest half step like a seasoned judge on a singing show. Photography opens another door. A mirrorless camera on a sturdy tripod can catch what your eyes cannot. Start with a wide lens to frame the star field, and take a series of short exposures, something in the range of a few seconds each. Then stack them with free software that aligns the stars and whispers the signal out of the noise. If you can piggyback the camera on a tracking mount, you can stretch exposures longer and reveal a tale that will not announce itself visually. Comets reward patience. They also reward snacks. Bring snacks. Now, the part where your backyard becomes a small node in a global network. Citizen science platforms accept visual estimates and images, tag them with time and place, and make them available to the community. Your observation, combined with hundreds of others scattered around the planet, fills gaps that professional telescopes cannot cover because of weather, scheduling, or geography. When a comet pulses in brightness with rotation, a chain of observers across time zones can stitch together a complete cycle in a single night. When a jet flickers, a quick report from one region can prompt follow-ups elsewhere. It is the nearest thing astronomy has to a relay race in slippers. Schools can jump in with minimal gear, a class set of binoculars, a teacher's laptop, and one clear evening can turn a textbook paragraph into a memory. Students can compare sketches, learn to star hop from a bright anchor to a faint target, and upload a joint report. They will discover an underappreciated truth. The sky gives extra credit for showing up. Even a negative report, clouds, or the comet too faint, helps build the record. Scientists call that a non-detection. Students call it honesty. Both are right. If your horizon is a mess of trees and streetlights, you are not out of the game. Many observatories run remote telescopes you can book over the web. You choose a target, pick exposure settings from a menu, and the robot does the midnight work while you sleep. The next day, you download your images, calibrate them with provided frames, and share results. It feels like magic, but it is just well-organized generosity. The galaxy does not care who clicked the button. It cares that the data is good. Etiquette matters. Do not aim lasers, do not trespass for a darker field, and do not blind yourself with phone screens between looks. Shield your screen with red mode or a piece of red film, and keep the talking down when someone is nursing a hard find. Comets, like birds, are easier to spot when the forest is quiet. Most of all, lean into the feeling that faint fuzz you record is sunlight bouncing off dust that left another star's backyard a very long time ago. You are adding a line to its diary. The professionals will stack that line with theirs, and together we will have a richer story. The motto is simple enough to write on a coffee mug: backyard telescopes, global science. In the next chapter, we zoom back out to the big picture and ask why collecting these lines in the diary matters. How every interstellar visitor refines our ideas about how planetary systems form and shed their leftovers, and how our sun's neighborhood fits into the galactic crowd. Chapter 17. Why this matters. Beyond one comet. Zoom out with me for a second. Our visitor is a single spark in a dark theater, but the real story is the firefly swarm we now know is out there. Interstellar objects are not rare miracles. They are the everyday leftovers of planetary construction sites across the galaxy. Every time we spot one, we are reading a postcard from another workshop. Stamps vary, handwriting changes, but the theme is the same. Planets are messy to build, and the cleanup crew throws a lot of ice and rock into the street. The galaxy, it turns out, is the kind of neighbor who always has a moving box on the curb. Why does counting these passers-by matter? Because numbers talk. The rate at which interstellar visitors drift through our yard tells us how efficiently other stars fling debris during their childhood tantrums. If we see only the occasional drifter, then most systems keep their leftovers close. If the sky is busier, then ejection is the rule, not the exception. That single statistic feeds straight back into our models of how giant planets migrate, how often small worlds collide, and how quickly infant systems settle down. Population science may not sound glamorous, but in astronomy, it is the secret sauce. Composition is the next gift. When one traveler smells like water ice and carbon dioxide ice, while another smells more like baked rock dust, we are peaking at different kitchens with different ovens. Collect enough recipes and patterns emerge. Maybe stars born in crowded clusters toss out icier bodies because radiation in those nurseries bakes surfaces differently. Maybe disks rich in heavy elements produce sturdier, dustier fragments that shrug off sunlight and keep flying. Either way, a catalogue of compositions becomes a census of how the galaxy cooks its worlds. It is like comparing breads from 100 towns and realizing which valleys prefer sourdough and which coasts love rye. Dynamics add another layer. The directions these objects arrive from and their cruise speeds are breadcrumbs that trace how our sun swims through the Milky Way's currents. If you map the trails of many visitors, you begin to see whether we are passing through a stream of debris from a particular star-forming neighborhood, or if the flotsam is truly random. That map tells us about the galactic environment, our solar system samples, over long spans of time. Think of it as cosmic weather, not rain and shine, but regions of space where leftovers are thicker or thinner, where the odds of a visitor drift up or down like seasons. There is a practical payoff for future missions too. You cannot design a good flyby or sample plan without knowing how often targets appear and how they behave. Do they brighten predictably, or do they throw dramatic tantrums? Do they tend to be compact and sturdy, or fragile and flaky? The more interstellar visitors we log, the more honest our mission blueprints become. It is the difference between planning a road trip with one restaurant review and planning it with a whole food blog. Interstellar objects also stress test our ideas about what is universal in planet making. If the same ices and dust show up again and again, that argues for common physics across many star systems. If we find a traveler that breaks the pattern in a convincing, reproducible way, that is a prompt to revisit assumptions. Either result is a win. Science is like a good editor. It trims what is ornamental, and it amplifies what is essential. There is a softer reason this field matters, and it has to do with time. These visitors are fossils on the move. They carry textures and layers set in eras far older than our continents. When we decode a spectrum or watch a jet flicker with rotation, we are reading notes left by disks that spun and froze before our oceans were a rumor. It is hard not to feel a little reverent when a faint smudge becomes a witness stand for the deep past. Grandparent energy, but now applied to the entire galactic family. Do these travelers ever deliver ingredients that matter for life? That is a spicy question, and we should handle it with oven mitts. The short answer is that they remind us how freely the galaxy shares basic chemistry. Whether that sharing ever crosses from inspiration to delivery is still an open problem, but every familiar molecule we see in an outsider is a nudge toward the idea that life's pantry is stocked widely. The universe may not be handing out recipes door to door, but it is certainly not hoarding the flour. Technology benefits from the chase as well. Rapid response observing, coordinating telescopes, stacking data, automating alerts, gets sharper with every object we track. The same pipelines that catch a shy interstellar visitor can catch near-Earth asteroids with better confidence. The muscle you build for a sprint helps your marathon form. In that sense, each interstellar campaign is cross-training for planetary defense and for the next era of sky surveys that will flood our inboxes with newcomers. Then there is culture. When people with binoculars log their own sighting and see their data plotted alongside professional spectra, the wall between expert and enthusiast shrinks. A field that invites the public to help count and characterize travelers is a field that stays healthy. Backyard telescopes, global science was not just a line. It is the operating system for this new chapter of astronomy. Finally, interstellar visitors pressure test humility. They remind us that our solar system is not the standard by which others are measured. It is one local example among many. Every time a new object cruises by on an open path, it is the galaxy tapping the glass and saying, "Look up, compare notes, keep score. We are not the main act. We are part of a very large festival." So yes, one comet is a story. A sky full of them is a curriculum. With each visitor, we sharpen statistics, tune models, and rehearse for the day when a spacecraft can meet one on purpose. Which brings us to the closing movement, how an idea scribbled in chalk became a checklist in control rooms, and how the next logical step is to send hardware to the edge of the stage and catch the traveling show in person. Chapter 18, The Ending Beat. From chalkboards to spacecraft. Picture a lamplit study 2 centuries ago. Wood floors, chalk dust hanging like a tiny galaxy. and a thinker drawing a curve that almost goes straight through the solar system without looping back. That simple sketch was not a prophecy. It was a promise that the sky would one day deliver a case that matched the line. Cut to now, consoles glow, antennas listen, and robots around a red world tilt their instruments to catch a fleeting visitor from far away. The chalkboard has become a dashboard. The old line has become a path you can plot on your phone. Earth is basically a rock that won the cosmic lottery, and tonight we get to cash in a curiosity dividend. This is the part of the story where the credits begin to roll and we realize how many names belong there. Observatory teams who pull dusk to dawn shifts. Students who write software that turns fuzzy dots into coordinates. Engineers who teach orbiters to look up from their routine and stare into the dark at just the right moment. People in backyards who nudge their tripods a hair to follow a pale smudge drifting between stars. If the 19th century gave us the melody, the 21st has handed us the orchestra. The score is the same, but now you can hear the woodwinds and the timpani. Think about the journey our understanding has taken. We began with an outline in chalk, a modest claim about what a true outsider should look like. We followed with telescopes that could catch a whisper of light and split it into a story. We raised the stakes with a world next door serving as a balcony, its orbiters and ground scouts turning curiosity into data. Along the way, we kept the tone that science likes best. Alert rather than alarmed, skeptical rather than cynical, thrilled without being theatrical. Photosynthesis is plants saying they invented solar panels first. Orbital mechanics is the universe saying the user manual came standard. The thrill, oddly, is how normal the strangeness turned out to be. An object from elsewhere behaves like an object from a real, physical elsewhere, not from a screenplay. It bends where gravity says bend, breathes where warmth says breathe, and keeps going when the geometry says the visit is over. There is a deep comfort in that, not because it is boring, but because it means the rules we have sweated over still sing when the instrument changes. You can haul a violin in from another town, and the notes still land true. And yet, beneath that comfort, the appetite grows. If we can turn chalk strokes into confirmed paths using ground glass and silicon, what happens when we add propellant? We can imagine a spacecraft that lives on standby, patient as a heron, waiting for the next visitor to appear, then kicking hard to meet it on the run. We can imagine a small fleet, one probe to map the coma in tight loops, another to watch the backlit spray, a third to taste dust just once. Carefully, like a chef sampling a sauce that simmered for eras, space exploration is not only about flags and rocks. Sometimes it is about catching a snowflake that fell from another cloud long before your weather began. There is a cultural beat here that is easy to miss. We are used to thinking of discovery as a private epiphany, a lone figure in a study, but the modern version is communal. A sensor in one hemisphere calls to another across an ocean. A classroom posts a measurement that nudges a model a little tighter. An operator sits in a quiet control room on a night shift and presses the key that gets you the image that will be in a textbook a decade from now. Curiosity scales. It always has. We just have better scaffolding now. And yes, there is still room for wonder without abandoning sanity. The wonder is that a body forged around another star can drift through our daylight and leave a readable trail. The sanity is that we know how to read it without turning it into something it is not. Black holes might be the universe's way of saying delete browsing history permanently. These visitors are the universe's way of saying keep the receipts. As the visitor fades, the lesson lingers. Old ideas, if they are good, do not retire. They find better lighting. A line scrawled in a book became a target list for surveys. A prediction about open paths became a checklist for flight teams. A hunch about chemistry became an observing plan that stretched from the ground to orbit and back to the ground again. We tightened the orbit, traced the tail, sniffed the light, and compared notes. The circle closes not with a period, but with a colon, More to come, because there will be more. Surveys are widening, software is quicker on the draw, and the network that passes the baton across time zones is only getting faster. More visitors means more tests of the principles we prize. Some will be icy minimalists, some dusty maximalists, some fragile, some road tough. One day, timing will do something outrageous, and a giant planet might nearly keep a traveler that clearly prefers the highway. One day, a mission patch will show a stylized streak and the words "First rendezvous with a wanderer from away." That patch will look very good on jackets. So we end where we began, with a line that does not close. The visit is brief, the lessons are durable, and the horizon is not an edge, but an invitation. We will keep the porch light on, we will keep the antennas listening, and we will keep the spreadsheets honest. Next time, we will be ready sooner, argue less about maybes, and push closer with machines built for the sprint. In the next chapter of this series, we can explore exactly what that sprint could look like: rapid response missions, smart trajectories, and how to design a chase for a traveler that never slows down. The chalk is in its tray, the spacecraft are stretching. Curtain rises again,